good morning. So, last time we talked about mass balances. We got to non-steady state stuff outside of just a batch reactor. So batch reactors are typically non-steady state. And I kind of fumbled a little bit and told you I'd come back to it. So we'll pick up here in a moment. I did have a question from an email about the example problem. So let me pull that up real quick and kind of just give a quick overview, clarify a couple things. So for the example problems posted, essentially we have three different segments down here at the bottom. So 1, 2, and 3. These are kind of approximately the three exams. For you guys, I probably need to add a little bit segment 2. So I'll try to do that. We ought to add some water softening problems there. So I'll try to get some more there for you. But to clarify, what I've done is I've shown examples. So like example 1.3 or whatever, versus the problems, and the problems are in the back of the book. So there's some of these, maybe there's not a problem 6.9, but there is an example 6.9, for example. So just wanted to let you know, and this is the sheet that's posted to Moodle for you. All right. Okay, so last time we were looking at how to derive a mass balance for non-steady state CSTR system, and we essentially got to a point for both cases where we needed something to help us out with calculus, right? We needed something more so than just the straight obvious, and I didn't have it on the top of my head, and so and I also had made a mistake here, by the way. This was right here we divided everything by V, I think, or no, we divided everything by Q. Okay, maybe that's fine. I forgot, I didn't see that. Anyway, moving on from that, I figured, okay, well, let's take a look at some of the methods that might be helpful. And so I was kind of reminding myself about integration by parts and then the U substitution stuff. And I was making some sense of it, but ultimately I was like, well, okay, well, what exactly does the book say? And so essentially the book describes these types of problems as step function responses, meaning we have some system, let's say we were at steady state and suddenly we add a whole bunch of stuff, or maybe we remove an input rate or something like that. So it changes the system, we have some disruption, and eventually we'll reach steady state again, but we were operating with some constant amount of stuff in the system, and suddenly we jump up, and then it's going to come back down to some other value, or maybe it could look like the reverse, where we're going sudden decrease of stuff, and then we're increasing from there. Whatever the case is, it's some immediate change in the operation, some change in the system, and then we have a time function that we're looking for. So really we need, instead of a mass balance where we had for a steady state, a mass balance was going to give us a function that was not dependent on time. Whereas anytime we have a non-steady state system, like a batch reactor, we have some time aspect, right? And so in our batch reactor system, we say we do the integration and we end up with a time value. So if it's a first order, it looks like an interest rate equation, right? It's like something times e to the minus kt, or we would substitute theta there. So it depends on that time. It'll keep going until we say, okay, here's the time we stop. For a So for a steady state system, we get those values that are not dependent on time. So the real question is, if we have a system where we have continuous flow coming in and going out, and then some sort of reaction, and then we perturb it and it's not at steady state, well, how do we figure out how long it takes to get to steady state? Or maybe we expect it to eventually get, let's say, from a concentration of starting of 100 all the way down to 5. Well, how long does it take to get to 25? We want to be able to solve equations that could give us that type of answer. Okay. So in our book, it's describing a system here, and it's going to derive the math for us for this system where we have basically a CSTR. We have some control volume, V. We have a concentration in it, C. We've got an input and an output. And then here they're saying we have two reactions in it. We have a decay coefficient in the text that tells us that's first order. And then we have a generation coefficient that tells us that's the 0th order. So in a sense, that's more complicated than what we've been dealing with, and more complicated than the examples I was aiming to derive up here. But in another sense, it kind of makes a little bit of sense, because if we just had one or the other, there'd either be infinite growth, and we'd never we'd never find a resting place for the concentration. It would never reach a steady state if it was just always growing. Or we'd have that risk anyway. So we'll stick with what they're looking at for a moment. So they have a first order decay and a 0 order growth. So it's like adding a set amount per time and decaying a percentage over time. Okay, so what they do, and I'll come back to this. I was going to talk about that. So what they're saying is, for this system, we have accumulation rate, V dc dt, is equal to the inputs minus the outputs, QC initial minus QC. Then they have the minus first order decay, so that's C to the 1 power, plus the 0 order growth, that's C to the 0 power. So all of that is in there, and just as we would expect. Okay. From here, they don't explain a whole lot. I believe I understand exactly what they're doing, but they're a little bit cryptic. So what they say is, okay, well, that's nice. And by the way, we can know the concentration at time infinite, which would be the steady state concentration, by solving it as if it was steady state, right? So C infinity is the steady state concentration of C. So if we let the system go forever, eventually we'll reach a steady state. And that's really like if we had a system that was operating and then we perturb it, and then it's going to increase up until some point with the new conditions, eventually it's going to reach this C infinity, right? The steady state concentration there. So the C infinity would be doing the system at steady state, right? So that's 0 equals in minus out plus whatever reactions we have. So how does that help us find our C of t, we could call it, or C at a given time? Well, if we think about it, in a system like this, it's kind of helpful to know our boundaries, right? We know where we're headed if we can just conveniently say, well, we could always solve it as a steady state, just assuming we gave it infinite time. That does give us a piece of information that can help us describe this system, this whatever equation could describe that function there, right? So in a way, it's kind of helpful, and we'll show this in a moment. it may be helpful to keep that in mind. And so they go ahead and solve this equation in terms of the concentration in a steady state system. They say this is 0 equals QCI minus QC minus VKD, the decay coefficient, times C, plus the growth coefficient times volume. And really all they do is they move both C terms to the left side, which would be, that would be QC plus VKDC equals QC. They're using I tend to use the little naught, plus KGV. From there, they factor out the C on the left and then divide both sides by what's remaining, which is that Q plus K decay times volume. Okay, so they just factored that out and said C times Q plus VKD. And then they divide both sides by that. Okay, so that's how they got this value. And I expect you should be able to do that. Okay, so that's, in terms of my expectations for you for the class, this is something that I would say should be routine. Going beyond this, I'd say at the moment, given the clarity I feel like I can give you today and the confusion I gave you last time, I would count like moving past this with this particular system would be something that maybe I'd give you as a challenge for extra credit or something to give your best shot on a homework or something. I would not give you the following on an exam. There are simpler systems, and perhaps if we revisit it and elaborate on some simpler systems, maybe that. But for now, that's just a little caveat. I expect you to be able to do this type of derivation to here. And then right now I want to talk about going beyond that to explore what we might do, what it might entail to do non-steady state, more complicated non-steady state systems. Okay, so we have the C at infinity. That's cool. We've got that. I'm just going to go ahead and finish this little part. Okay, so that goes there. Okay. So now what they say is, well, this dc/dt term from up here, if we rearrange it, we can actually factor out some function of C at infinity. And here's, I think it's just algebra what they do, but it's not intuitive to me how they extracted the C minus that term when solving this equation. Because what they're doing is they're solving this equation, getting it in terms of dc/dt equal to stuff, and from there they factor that out. The C minus, what's essentially C minus C infinity, because what they did is they substituted in here for that. So they made this substitution. This is an algebra step, and what that lets them do then is say, well, we've got all these terms, the K's, the Q's, the C initial, all of that, we can get some information about that by solving it as a steady state system, which does kind of make some sense, right? When I talked about that a minute ago, this equation, this function should have some reference to this asymptote that it's approaching, right? So we do expect that should work in a way, even if it wasn't straightforward and obvious to us why to go ahead and just magically extract all that out with algebra. Okay, so given that they did that, let's take a look and see how they progress. So now they have dc/dt equals this negative q over v plus kd. I guess that's what's left after extracting and simplifying, times this C minus C at infinity, which captures all that information. And then they say, okay, well, let's do a change of variable. as a way to approach this integration. So instead of saying, let's try to get just that c by itself, let's just call a new variable y equal to c minus c at infinity. So it's going to incorporate those constants, and we can just treat it and integrate it that way. And so when they do that, they say, if we say it in that manner, because c is the only variable in that term, everything else is a constant, and we can actually say whatever dy dt is should be the same as dc dt, is essentially the claim there. So with that, they say, okay, well then dy dt is equal to this negative q over v plus kd, coming from there, times y. And that's a much easier system to deal with, because then we're just trying to integrate on y, and we can move that to the left side, and so we get dy over y equals this stuff, the minus q over v plus k d dt, and that's just constants, and we integrate the dt. We do that from 0 to t, and do this from y naught to y. Like they just set it up right here, right? So just get that out of the way. So, and that's something we definitely know we can do. We've already done for the batch systems, first order batch systems. So we know that that's going to yield y equals y naught times e to the minus kd plus q over v times time. And then from there, we can go, so this is just marching in this order here. From there, we remember that, okay, we have that expression for y is equal to c minus c at infinity. So the initial y then should be the c initial minus c infinity. Okay, so that's how they deal with the y initial. And from there, they plug things in and say, okay, well, c minus c naught, or excuse me, c minus c infinity is equal to c naught minus c infinity times e to the minus that stuff. And finally, they say our ultimate function for c, after separating all of that, just looking for c, is equal to c at infinity plus the c initial minus c at infinity, all that times e to the minus kd plus q over v times time. If we do look at the units up here, this is per time, and q over v is inverse of our hydraulic retention time, so that's also 1 over time. Both of those times time gives us a unitless exponent, which is great. So we don't have to worry about that. Good thing to check though. So at the end of all this, they've given us an equation, and what's interesting to me is that this the generation term, the kg, has in a way disappeared. It's not in that final equation, except that we can use it to figure out, or we have to use it to figure out the c at infinity. So there's some interesting simplification there. I was able to work out a very similar process for the zero order simple case. I'll walk you through that, and we get something that looks a lot like this. And so I think it's probably the right way of doing it. But again, I'm not comfortable enough with this and the way I've taught this to give this to you on an exam. Right? So I'm not planning to give this to you on a formula sheet unless I decide to revisit it and we practice it some more and we all feel good about it. Does that kind of make sense though, their process there? Okay. So I think the deal is it's just a matter of understanding how to do the calculus part well enough, right? Because we should all be able to derive an equation given a mass balance. And then the thing from there is, can we integrate that equation and have a correct solution? And that's where I'm saying I want everybody to know that that is possible, and we will do that for some systems where it's reasonable. But let's say you're out working in the field, a few years from now, and in the industry or something, and you come across a problem. You should be able to realize, oh, we can solve this. We just need the right tools, right? Because then that's the important information. Is somebody knows how to do this. Let's go figure out who that is and apply it to this case. Okay, so coming back to our zero order decay equation, let's see if we can put that same C at infinity logic into play here. So this is going to be our mass balance when it's at steady state, right? So if we solve a zero order decay reaction at a steady state system, we have 0 equals our inputs. And again, this is for a CSTR we're talking about. So we're going to say this is going to be QC initial minus QC final plus whatever reaction, and this is just a zero order decay, so we have minus VK here. So we solve for C, we can just add the QC to both sides. So QC equals QC naught minus VK. And then that gives us C equals C naught minus V over Q, which is theta K. So then we can say that's C at infinity, right? That's the way we get it. And you'll see it in problems when we're reading a word problem or something. A lot of times it'll say it's been operating for a very long time. So that gives us that hint that essentially what we're dealing with is the steady state system. Okay, so let's keep that in mind and see if we can extract that piece of information out of whatever derivation we're doing here to simplify our integration. Okay, so with non-steady state, we have V dc dt equal to the QC naught minus QC minus VK. So we can go ahead and, well, we could divide everything by V here, although if we're looking to get a value with theta K, that might be kind of the simpler way to think about it, or perhaps V over Q, could rewrite it, either one. Then when we do this, I'm actually kind of interested in trying to solve my algebra in such a way where we have that V over Q on the K here. So what I'll do for now is I'll just say dc dt, we'll go ahead and divide everything, but I'm going to leave it kind of obvious by just leaving it in the terms each time. So let's see, not. Even here, I'm going to say just V over V times K. And from here, we can maybe recognize that in order to get V over Q on the K, we need to extract, we can divide all these terms by something, by factoring something out, right? So we can say dc dt is going to be equal to something in order to get a V over Q here. So if we extract out a, let's see, we'd have to have Q on top so that on the inside we divide everything by Q. So that's going to give us a Q on the bottom here is what we want. Over V, that's going to leave us the V here because essentially that'll counteract the bottom one will take it out of there, right? So that leaves us with V over QK, which is what we want. And if we take the Q over V out of the other terms, it's actually very convenient, right? Because we just factored it out directly. So we're just left with C naught minus C minus that, V over Q times K. Does that make sense? That just several factoring out things here. So it's algebra, and I believe that what we were looking at the book doing a minute ago with that more complicated system, I think that's all they were doing. It just was not as intuitive to me when I was looking at it last night. Like this whole term to factor, well, it's to C minus that, right? To factor all of that out, maybe if I stare at it longer, it might start making more sense. But I'm pretty sure that's all they did here. So now we're very close to having the C at infinity, right? So we have dc over dt equals that stuff. So let's see if we can formulate this in a way where we have c at infinity as a term here. So we say dc dt equals c naught minus vk over q. So that's actually c naught right here and vk over q here. So we could say this is q over v times c naught minus v over q times k. That is our c infinity minus c. And that's starting to look a lot like what the book was showing us for this problem, right? They extracted a c minus c at infinity by factoring out this stuff, q over v plus kd. They also factored out a minus term, which that's how they flipped this. So let's go ahead and extract out the minus term as well. So let's say that's minus q over v. Then we have c minus c at infinity, just to be very, very close to what they did. Okay, so now if we say, let's call this y equals c minus c at infinity, then we should be able to integrate this when we put it into place. So, and we'll say dc dt equals dy dt. So here, then we could say dy dt, we'll let me write, is equal to negative q over v times y. So we do dy divided by y equals negative q over v dt. And we can integrate. So essentially that's going to give us natural log of y over y naught equals negative q over v times t. That'll give us, running out of space here, I'm going to erase a little bit. So we could rewrite this as y equals y naught times e to the negative q over v times time. And just as a quick check, q over v, that's again the inverse of our hydraulic retention time. So that's 1 over time times time gives us a unitless exponent there, which is great. So then, now we can put in our terms and say, and replace back, instead of y, we take c minus c at infinity. So c minus c at infinity is equal to c initial minus c at infinity times e to the minus q over v times time, which is kind of interesting that we end up with this exponent for a zero order equation. Although you will notice we don't have the k in here. So the k is used when we solve for c at infinity, but not in here. And I think, just like we saw in the last problem, I think that's because it's a zero order equation. Even though the whole system is acting exponentially because we changed something and it's a continuous flow, it's gradually going to come back up or go back down or whatever. So it's got that gradual component, but the rate constant itself is not a function up here. So I think that actually matches pretty well. So if we solve all this finally, it should be c, we can add the c at infinity over here. So just c at infinity plus c naught minus c at infinity times e to the minus q over v times time. Okay, and I believe that would be the correct solution to what I tried to do in just a little bit of space last time. Does that make some sense? That process looks maybe reasonable. I mean, when I say reasonable, like logical. not that I'm I'm not planning to give you something with that depth as like a fifth problem on an exam or something. Okay, so let's take a look real quick, just comparing that to this solution. Really, the only difference here is that KD and that exponent. It's a first order. That's the only thing that's different in what we derived here. It's got the c at infinity plus c initial minus c infinity quantity times e to the minus something times time. That something was q over v for us for the zero order, and for them it was kd plus q over v. And then part of the solution contains that information about what happens at steady state, which gives us that role of the k that we had went into that c at infinity, right? Because that was our mass balance. In their case, that was not only the k for the growth, but also the k for the decay, both of those terms. And for our simpler case, that was our k here, right? So all of that information was contained in the final solution, even if it wasn't directly obvious. So we could substitute in for each time we see c at infinity, we could substitute in these values. It'll get a little messier, but maybe it would help us feel a little better, like all the pieces are there, like we would have expected. Okay, so that makes me think that this solution here is a bit more general than I would have thought at first. For CSTRs with some sort of a non-steady state condition. So we will possibly come back and explore that. I know that there is a decent homework problem that I plan to assign at some point that talks about a stomach as a CSTR. It's got a little bit of acid pumping in, it's got a little bit of food pumping out, and you eat a hamburger and suddenly that's a sudden input of mass. And so then we have like a starting concentration, and then we're tracking the mass over time. How long does it take to digest? And so then it becomes a non-steady state system. And for that one, I'm pretty sure the math is simpler than all of this. So we will come back and talk about this some more. For now, I'm just going to leave it at that. I was trying to derive the first order in the same manner, and the this step where we extract the c minus c at infinity just was not intuitive to me, so we're going to leave it here for now. Cool with that? All right. Okay, so we talked about second order last time. We talked about the derivations. We can have these tables and a bit of a cheat sheet of sorts for none. So anytime n is not equal to 1, we can have kind of a general general equation if you ever did have to deal with a system that had like a partial order equation that was strange. So that math is out there. We did this problem last time, and that was our solution. And so from here, I want to pick up at this point where we talked about deriving rate constants from empirical data. Like we already have data, but what we want to know is what is that rate constant? So we did an experiment in the lab, and we have some data to work with. How do we get that K value? Because that's an important process. So we talked briefly about it last time, but this time I brought some data so that we can play with. Okay, so a bit of experimental data here. Essentially, we did a disinfection experiment where we were killing some viruses that act as a surrogate for pathogenic viruses. It's nice to work with these viruses because they only prey on bacteria, so they're not going to hurt us if we accidentally were to be exposed. They might hurt E. coli if we had E. coli. So in fact, we probably do have E. coli in our gut, so if you did, let's say, ingest some of this virus, maybe that could disrupt your stomach stuff a little bit if it did infect those E. coli, but it wouldn't be like actually attacking or infecting you yourself. So it's a pretty benign type of thing to work with. So anyway, in our lab, we are able to count these by infecting E. coli and then counting, like looking and finding, okay, well, how many spots did the E. coli get decimated by this virus? So it's kind of brutal if you think about it. This disinfection experiment where we are feeding millions and millions of E. coli to these billions and billions of viruses. So it's like a complete slaughter. And then add to that, we're like destroying so many viruses and just seeing what happens, doing a microbial genocide here for experiments. Good thing we don't have any ethical concerns there. Okay, so we started with 2.9 times 10 to the ninth virus particles per milliliter, essentially, or something like that. And so that was our concentration. That's this N over N naught so this is really the average N, actually, should say. And then what we want to put in this part here is a log of N over N naught. So if our initial concentration was 2.9 times 10 to the ninth, and then 2 minutes later, we were down to 5.4 times 10 to the fifth. There's a question about, okay, well, what does that look like with the kinetics? So let's go ahead and plot that. And it's immediately clear that our kinetics are like, it drops so fast. And that's because we have a linear y-axis over here. Okay, so if we were to zoom in, let's say just for the sake of watching what happens to the graph, if we delete this one, we see that now all the rest are a little bit in frame, and we can see what's happening with those. We could even delete the next one, and it readjusts, and we see it's sloping like that, right? It's just kind of hard to see on this one graph. So I'm going to undo that, but we recognize, okay, well, it's not linear. It does look logarithmic or exponential. So that's a good sign. So what happens if well, there's a couple things we could do. We could convert these numbers themselves into a logarithmic form, which I will do. The other thing we could look at is if we convert the y-axis itself into a log axis. That should then show us a rather linear form. So if we format that axis and do that, log scale. Okay, so it still does not look linear if we plot it on the log scale. Actually, that makes sense, and I'll explain in a moment. But with the log scale, we can catch everything on our viewing window at least, right? So we see that it looks that way. So what we want to do to truly transform the data then is, like, because this is the raw value, we did a couple experiments and this was the average of the two and of the different plates we took. So here's our data point, and what we want to say is, what about the, and typically we would do natural log if we want the k specifically. If we're just plotting like how many log reductions, sometimes we do logarithmic. Just to show, is it 99% or 99.9% or whatever. We'd actually have to factor back in the natural log compared to the log base 10 to get the k. So I'll just, either way it should be linearized because we've log transformed it. So we'll do 2. We'll say the natural log of n over n naught. That'll give us the actual k value. So this is the k. This one will be log. Okay, so all we have to do is say this is going to be equal to the log of our current n for that time divided by the initial n we started with. Is a neat little Excel shortcut. If you had just placed a cell like C6 here, and you want it to freeze, you can hit F4, and it'll automatically add the little dollar signs to be that. You can hit F4 a few times, it'll cycle through. Is it just the number? Is it just a letter? Is it both or none? Just by hitting F4 is kind of cool. So I'm gonna go ahead and do that. So freezing that first one, so anytime, even if I fill this downwards, anytime I call the, essentially what that'll do is say, for this time it's C6 over C6, cell C6 that is, and when I fill downwards, it'll be then C7 divided by C6, and then C8 divided by C6, and so on. So a neat little trick. We can do the same thing here, the natural log of C6 divided by that. And this should actually look quite similar. Of course, the natural log is different than a base 10 log, but it's close enough. Okay, so I'm going to move this aside, and then we'll see if we are linear when we create a new graph. Oops. Okay. Really? Sorry, my on my window, my my picture of myself is kind of getting in my way. Let's see. All right. Try that again. Okay, so now we have this, and the data is still not quite linear. So I think what's going on is I just thought I grabbed linear data, and I didn't. on the graph I was looking at when I was grabbing this data, it was the plot made it look pretty linear, and we could add a trend line and see, okay, well, is this close? Maybe with error bars. maybe that would make sense. So we'd probably want to set the intercept at 0, and then check all that. So 0.94, definitely not the best, not super linear. One thing that does happen sometimes with these particular experiments is we get down too low and it's sort of below our detection limit or something. So sometimes I'll take a look at these when I didn't have all of the data, like I removed the last one or something. And then we can see, I'll do this. We could then draw a new line and see if that changed anything. But okay, this would be the process. And I realize I didn't bring the best data, but that would be the process. It should be linearized if it's a first order. So what I see here is it's not actually first order, at least not for the whole time. Maybe the first minute is first order, and then we have some tailing. So, for example, if we deleted these two, and we took more data points along inside there, maybe that's first order. That's cheating the data, though, so we're not going to do that. All right. So enough of that. I will see if I can get a better data for you to work with on a homework problem or something. Okay, but we talked about that in terms of what that would look like, for a system going from something like that to a linear system, and we can extract the K. And that would be the process to do it in Excel, is to do that transformation, do the line to best fit, and then you have your essentially, and I set the B to 0 because the n over n naught should be 1 if it's n initial over n initial, right? And so that means the log or the natural log or whatever of 1 should be 0 always, right? So we can set the intercept to 0. That makes sense. And then we have a y equals mx. Okay, so with that, I'd like to talk a little bit about drinking water. So get into the meat and potatoes here. All that about reactions, reactors, all that gives us a lot of the fundamentals I wanted to make sure we're all up to speed on for any type of water treatment system that we're going to apply. Whatever the technology, we're going to need the material balance of some sort. Ultimately, for drinking water, our fundamental motivation is to protect whatever we're going to ingest to make sure it's healthy. So that means I don't want anything nasty in the water I'm about to drink. And I want to make sure that we have multiple safety nets in place to prevent that. And ultimately, there are toxics and things we have to be careful with or concerned about. But really, in general, and I guess most of the starting point for water treatment is really to eliminate the fecal-oral route of transmission. So this would be for microbiological purposes. Essentially, what we need to realize is if we have some river and we want to take some water out of this river to drink, we're going to have some extraction, and then we'll put that into our cup or bottle and drink that. What we need to be concerned about is, well, what's happening upstream? Because usually somebody's making use upstream, and as unfortunate as that is, usually some sort of fecal matter is going to make its way into our water source. Or maybe it would be good to assume so. Not only that, but maybe there's some sort of animal here. We'll just do a nice little stick figure. Maybe give it a snout and some ears. Sure, some eyes. Well, whatever animal that might be could also, beautiful drawing here, might also be adding fecal matter into our waterways or into whatever system we're trying to extract water. So in terms of big picture stuff, drinking water treatment, we want a barrier right here. We'll say drinking water treatment. to prevent any of the nasty stuff from getting in. The other barrier we tend to have would be a wastewater treatment system. So if we're draw it that way, we would have this would be our wastewater treatment. And that's not going to be enough because we know there's animals in the wild, and who knows what's going to be in our water, right? So that's the fecal oral route of transmission. Sounds pretty gross. Turns out that's pretty much also the way you get pink eye, is some sort of bacteria that likes to live in a warm-blooded animal's gut. That's typically where they thrive. Gets into your eye and starts multiplying and just kind of feeding on whatever organics it can find. And it's an infection that would be typically fecal originated. So you're dealing with a lot of young children who are not the most hygienic little organisms, or maybe swimming in a body of water that's got a lot of bacteria in it from said sources. That's probably a very likely cause of pink eye. Okay, so if we think about it, we could get our water from a lot of different sources. And depending on where we're getting it from, it's really going to dictate what kind of treatment we need. If you had the luxury of access to freshly melted glacier water, it's never been anywhere near an animal in its present form. It was evaporated into the atmosphere and then deposited on top of this mountain or something, and it's just really never been anywhere near an organism, and you can just drink that all day. Maybe you're fine. Maybe you don't need any treatment. There's some chance maybe there's atmospheric pollutants or something, and maybe it would be good to have some carbon filtration or something. But if you compare that to trying to drink out of the Mississippi River, it becomes pretty obvious that there's going to be some differences, right? Even here, where we have the Mississippi, great body of water for a whole lot of water there, we actually decided to take from the groundwater because there's some natural filtration that's occurring there through the porous media that is the sand and the soil. For some cases, your treatment or your decision on that is really going to depend on kind of the water supply and where in the water cycle you are. We could even use seawater if we decided it was worth the energy cost to desalinate. So it really depends. So our treatment operations are going to cater towards where we are with all of that. So a typical water system, an engineered water system in an urbanized environment, would look something like this. We have a variety of options to withdraw from. Could be a reservoir or a lake, a stream or river, could be groundwater. We'll take one of these sources, typically, and send it to the water treatment plant. From there, we have a water distribution system, and I would say that's, in a way, part of the treatment operation, because it needs to carry enough residual disinfectant, needs to be maintained, and it typically is under the purview of whatever municipality is providing that water treatment. So that really is often described as part of the water treatment system. The Flint water crisis is a good example of that. We will talk about that, but essentially, since they were not operating their water treatment plant properly for corrosion control, the distribution system that was fine previously suddenly became a massive issue, leaching lead into their water. There were many other problems at the same time as well. So then that'll ship the water to maybe industry, maybe to different homes for domestic water use, and then whoever's using it is going to create some wastewater, and that then has to be sent to a wastewater treatment plant. In the past, sometimes people would connect, or I guess municipalities would connect storm sewers, and they say, well, we've got all this runoff from the roads and junk. Maybe we should treat that before sending that into a river or whatever. And so they used to send those into the sanitary sewers, into what would be called a combined sewer system. Turns out that's a pretty bad idea when it floods or rains, because then you flood your sewer systems and then you've got sewage flooding everywhere. Pretty bad. So maybe a good thought at first, but in practice, not at all good. So lately, everything's been a storm separate sewer system. So if you ever hear about that, I think in Baton Rouge, we pretty much have everything separated now. When I was in Michigan for a couple of years, they were still working to separate different pieces. And so then for treatment of stormwater, usually what you want to do is just let it settle, like give it some retention pond or some retention tank of some sort to get some settling action to get rid of some of the sediment, so you're not overloading whatever lake, stream, or river with a bunch of sediment, and then that actually improves the water quality pretty good for the sake of natural systems. So then you typically would then discharge either to the groundwater or to surface waters, all that water that you've just treated. So in the class as a whole, we're really interested in kind of what's happening between this side and this side. And really, that interconnection here is important, because while you might not put your own water intake downstream of your own wastewater, somebody's probably living downstream of you, right? So, and somebody's probably living upstream of you. So these interactions are quite important. So that's all kind of bringing us back to the connection here, water and wastewater, quite important. Okay, so one of the big milestones for disrupting that fecal-oral route of transmission was really the advent of chlorination. And it wasn't like everyone everywhere immediately started chlorinating in the US, but here's a decent graph that's just showing death rates for typhoid fever from 1900 to 1960. And chlorine was very likely a significant part of that, as we see there may have been some decline beforehand as we learned more and had better health care. But with chlorination, typhoid fever is a fecal-oral transmitted disease. In fact, if you travel to less developed countries, then a lot of times you'll be recommended to get a typhoid vaccine in order to avoid a kind of worst case for, what is, the fecal-oral transmission of organisms is more common if there's not very good protection for your water systems and your food systems. And so when you travel, it's still a risk in many areas, and it's one of the worst outcomes. Obviously, people used to die quite a bit from it, but even as of 1950, the death rate per 100,000 people was near zero. So just a good case example there. Okay, so from a regulatory standpoint, most of our drinking water standards are driven by the Safe Drinking Water Act from 1974. This gives us national standards for a variety of toxins and pathogens, and we can really, I guess, best understand the regulations as a whole in terms of primary and secondary standards. Primary being the ones, I think I touched on this on our first class, that really have to do with health. So these are enforceable, meaning they are mandatory for public water systems. And that's something I'll note here. This is for public systems. I think there are recommendations that all private systems ought to meet these, but I don't think there's any regulatory capacity to force that on private systems, right? You can, if you wanted to drink from the LSU lakes, that's your free choice. You are free to do so. So I guess you could use public property in that manner, or if you had a pond in your own property and you wanted to drink from it, that's on you. But if a public municipality that's a government entity is going to serve you water, it better treat that water to these standards, right? That's kind of the thing. Otherwise, we get mad and we sue the EPA or whoever. So that's why we have standards in some sense. Kind of funny that it works that way. So these are enforceable. They deal with chemical hazards, radionuclides, so any potential radioactives. I mean, that could be considered chemical. We, I guess, talk about it slightly differently because it's a little bit of a different mechanism, a little bit more physics there, and microbial. So this would be our pathogens. We also have secondary standards. These are predominantly aesthetic in nature and not enforceable by definition. So these are things like the taste of your water, the odor, the color, the temperature, and what we call hardness. So if my water here was tinged with brown, brown color, might not look too pleasant if it came out of the tap and it was warm and kind of smelled bad and it was brown and it just did not look very good. That might meet all the regulations that it had to. It just would be not meeting the recommended standards for the aesthetic qualities. So if that was, it is possible that would be perfectly safe to drink, right? But it would also be possible that would be gross and I wouldn't want to drink it, right? So then that's where the secondary standards come in. It's not that they're enforceable, it's that there are some guidelines that, hey, people like it if it is not brown. You've got nice clear water that doesn't smell too much like sulfur or chlorine or any of that. The chlorine, there are specific chemical and disinfection standards that has to keep. Hardness is an interesting one that if you've ever lived in different places or traveled to different places, you might have noticed the way the water interacts with you if you are washing your hands with soap or taking a shower with soap or whatever. Like the way the water interacts with soap actually depends on how much mineral content there is in the water. So as a quick little example, I grew up and spent much of my life in northern Georgia. And then for a couple years, I was in Michigan, right around here. And then I moved down here to Louisiana. And so if you look, and depending on the precise spot that I drew those, I've experienced for most of my life pretty soft water. If this is our hardness scale here, with 0 to 60, that's the purple, 0 to 50 rather. And this is, we'll talk more about this later, but this is milligrams per liter of calcium of hardness as Ca. That's the way we quantify it. Once we get to that section, I'll elaborate more. But so that's what these values are. So anyway, 0 to 50, that's pretty soft water. And then up here, it was 100 to maybe, so that was hard, maybe very hard, depending on where I was getting the water. And then back to Louisiana, where probably in Baton Rouge, I'm guessing we are kind of in that soft range. But if we get towards New Orleans, then we're getting to that harder water. So depending on where you've been or where you grew up, maybe you were on groundwater of some sort that was harder, or surface water could have been hard or soft or whatever, depending on all that. What happens is for soap, if you've got a lot of calcium, just Ca2+, that affects the way soap molecules work. So a soap molecule is a surfactant, meaning it's usually kind of squiggly, and it has some charge on one side, maybe some minus, and some kind of less polar side over here that's going to interact well with hydrophobic stuff like oils. So it can interact well with water on the charged side, and interact well with like other stuff on the other side. So it forms these nice bubbles and things, and several different properties. But essentially, if you've got a whole lot of calcium, that's going to satisfy all the negative charge on soap. And so they all sort of bunch up together, and it kind of makes the soap less effective. So what's interesting then is you need more soap if you've got hard water, or if you've got super, super soft water. It's really hard to get it off once you have it on, and it feels like you're just always trying to scrape and get the soap back off of you, and it's like never going away, because it kind of feels like there's a film there, because there's none of this happening, and it just has this kind of layer. The water interacts with surfaces differently, so it's quite interesting. So anybody seen that before or noticed this? No? Yes, maybe a little bit. The other thing that you'll see is calcium deposits or mineral deposits on the sinks and stuff. If you have hard water, anywhere there's a little bit of standing water or like splashes around the sink or the bottom of the sink, you'll start getting like kind of brownish mineral deposits much more common or frequently than when you have soft water. So mineral deposits and scaling has an impact on some industrial uses as well. But those are typically like I guess some of the aesthetic things that are kind of interesting that you don't notice when you drink the water necessarily, but just another interesting phenomenon. And we'll cover that in our water softening portion. Okay, and maybe I can do some sort of a demonstration, make some hard water and watch what happens with the soap. Okay, so where do we start for treatment? And I'm just going to give the overview here, and we will actually get to these things next time. So we've got a couple people online, and one said, I've noticed the deposits in Minnesota because of how hard the water is up there. So like just mineral deposits. And if we take a look, yeah, definitely lots of, not a whole lot of soft water up in the Northwest or Midwest, I mean. Interesting. Okay. So for a typical drinking water treatment process or train, I guess we'll start with what we would use for a surface water, kind of a generic surface water we're getting from a lake or a river or something. We're going to want to pull from our source, screen the water with some physical bar rack, get out the tree limbs, the basketballs that are floating in the river, whatever junk that's there that can be separated, just shouldn't ever come into any of the plumbing. So we pull it through some sort of a screen first, and then usually we'll have some kind of a grit chamber to catch whatever sand particles, whatever little pebbles might be coming through that could mess up our machinery. So that's a way we can kind of rapidly get rid of some of the larger stuff that could disrupt our pumps and things. Then we come to primary sedimentation. We use gravity. Gravity is great. It's pretty much free. We just have to let it sit there for a little bit. So we design a chamber to let gravity do as much work as we can. Then we're going to enhance gravity's effect by adding a coagulant, mixing that up real quick, letting that coagulant take effect. Coagulant is something that causes different particles to stick together, create larger particles. Those settle faster. That'll be kind of our first unit, is talking about sedimentation, coagulation, flocculation. So then we use gravity again. We're getting all these particles to settle. And then we want to do some sort of filtration typically, because the sedimentation is great, but it doesn't quite get all the particles. And if we've already destabilized them with this process, it's a good chance we can just use like a sand filter or something to let these particles then stick to all the other components there. So typically we'd have some sort of like sand filtration. Then if we're good at that point, then we just go ahead and dose with disinfection, give them adequate time in the disinfection reactor. So that contact time that we want, and then possibly add fluoride. and send it off to the users. So that's a pretty good picture of the different treatment processes we are going to cover. We'll also discuss if we do add some sort of softening step, that would come in probably here before disinfecting. Okay, so that's all I've got for today. And have a good Labor Day. I'll see you guys on Tuesday. Any questions? Anything? All right. Have a good weekend.